Good morning, students. Myself, Vijay Shankar from DC Department, Chebol Engineering College. Today, we are going to discuss about a new topic in the second unit, transmission lines 2. That is a 8th wave line, quarter wave line, and the half wave line. Lambda by 8 and lambda by 4 and lambda by 5 length of the transmission lines. So first of all, you can see the 8th wave line. 8th wave line means is a lambda by 8 length. Let lambda be the wavelength of the transmitted frequency f. Consider a transmission line of length lambda by 8. Let us assume this is a transmission line. At load end, there is a ZR. At input side, that is a Zin. And the Vs is also there. The Vs is a voltage and Is is a current. And output side at the load end, IR and the VR. Here it is denoted as a ES and the ER. And the length of the transmission line is represented as a S or the L. L is equal to lambda by 8, or it is a S is equal to lambda by 8. So given as a S here. Length of the transmission line L is equal to. The generalized expression of for the input impedance is given by, we know the ZS is equal to, or the Zin is equal to Z0. Actually, we know that ZS or the Zin is equal to Z0 into either ZR plus J Z0 into tan beta L whole divided by, and Z0 plus J ZR into tan beta L is the equation we derive in the theory part. When we discussed in the transmission line, Zin is equal to Z0. Here the Z0 is equal to ZR, not the ZR. Z0 is equal to R0, and L is equal to, here they're representing in the textbooks as S. Nothing will happen. So both are the same here. How we get the beta L? Actually, the ZR into cos hyperbolic or cos beta L and sine beta L, Z0 into cos beta L plus J ZR into sine beta L. Okay, and alpha is equal to 0 there, and gamma into Z. The gamma, the propagation constant gamma is equal to alpha plus J beta. Okay, cos hyperbolic J beta L, cos hyperbolic J beta L is equal to, we got the cos beta L and sine hyperbolic J beta L is equal to J into sine beta L. Okay. So actually Zin is equal to, we know the formula here, Z0 into ZR cos hyperbolic gamma L plus Z0 into sine hyperbolic gamma into L whole divided by, and Z0 into cos hyperbolic gamma into L plus ZR into sine hyperbolic, actually it is a px, not the gamma. in the transmission line, the propagation constant is representing as a P. The gamma is also the propagation constant, but in the transmission lines, we use P is a propagation constant. Actually, it's a Px, x is equal to L. X is the distance of the transmission line, x is equal to L. Then let us take this also the x value. Cos hyperbolic Px, sine hyperbolic Px. So the P is equal to the gamma, not the gamma, the P is equal to alpha plus J beta. When alpha is equal to 0, the lossless transmission line, P is equal to J beta. Means when it is a cos hyperbolic P as J beta into x, x is equal to L, J beta L. Cos hyperbolic J beta L becomes a cos beta L, and sine hyperbolic J beta L becomes a J sine beta L. And take the both the numerator and denominator as a cos beta L is a common. Sine beta L by cos beta L is a tan beta L here, and Z0 plus J into ZR sine beta L by cos beta L is a tan beta L. Okay, I think you hope everybody know that how we got this expression ZR plus Z0. So in the Z0 here they replace the Z0 is equal to R0. What it matters? You know the beta is equal to 2 pi by the lambda in terms of the lambda, 2 pi by lambda. Lambda is a length here. Okay. L is equal to lambda by 8. Given that the length R, it is a S is equal to lambda by 8, 8th wavelength. Okay. It can substitute in the beta is equal to 2 pi by the lambda is equal, L is equal to, or S is equal to lambda by 8, and beta is equal to 2 pi by the lambda. So Zin is equal to Z0 or it's a R0 into ZR plus J into, here the Z0 is replaced as R0, tan beta, what is the beta value? The 2 pi by lambda, 2 pi by the lambda into S or L is lambda by 8, and whole divided by, and Z0 write as R0 J into ZR tan 2 pi by the lambda as a beta value. We assume the length of the transmission line is a lambda by 8, 8th wave line. Lambda get cancelled here, and 2, 4, 8. So Zin is equal to R0 into ZR plus J into R0 tan pi by 4, 45 degrees. R0 into R0 plus J ZR tan pi by 4. So tan pi by 4, we know the value is the 1. So Zin is equal to R0 into ZR plus J into Z0. Tan pi by 4, the value is a 1. Tan 45 degrees is a 1 value. And R0 plus J into ZR into 1. Okay. And still, finally, the Zin is equal to, in terms of R0 and ZR, R0 into ZR plus J into R0 whole divided by R0 plus J into ZR. Okay, we got the Zin is equal to in terms of the two functions. Eighth wave line, the Zin is equal to R0 ZR plus J into R0 by R0 plus J into ZR. Okay, and ZR also you can write as RR in terms of the resistance only. So Zin is equal to R0 into ZR as RR plus J into R0 whole divided by R0 plus J into RR. Okay, all the values are now in terms of the resistance only, not the impedance. ZR is equal to RR and Z0 is equal to R0. Okay, take the numerator as is a complex function. Take the numerator as a magnitude and denominator is also complex function. Write the magnitude of the value. Its magnitude is RR plus J into R0 is the square root of imaginary square plus the real square, RR square plus R0 square, and in the denominator also R0 square plus RR square. So both are get cancelled. Zin is equal to Zin, only the magnitude of the input impedance is R0. Thus, the eighth wave line is generally used to transform any resistance RR to an impedance Zin having its magnitude is equal to the characteristic resistance R0 of the line. So in the eighth wave line is generally used to transform any resistance to an input impedance having its magnitude is equal to the characteristic resistance R0 only. The magnitude of Zin is equal to what it minus points. Finally, the magnitude of the input impedance Zin is equal to R0. Its magnitude is equal to the characteristic resistance R0 of that line. In eighth wave line, generally used to transform any resistance RR to an input impedance Zin having its magnitude is equal to the R0. Now, next one is a quarter wave line impedance. Quarter wave line, that is, we can call it as a quarter wave line, is also called as input impedance matching. It's the same equation. You can take Zin is equal to Z0 into Zin is equal to Z0 write as R0 ZR plus J into R0 tan beta L, or is a beta S. S is the length of the transmission line. Consider here the transmission line length is a lambda by 4, quarter wave line lambda by 4. R0 plus J into ZR tan beta X tan beta S, where S is equal to lambda by 4 and beta is equal to 2 pi the lambda. Okay, substitute these equations in the Zin. Zin is equal to R0 multiplying with RZR plus J into R0 tan, what is the value now? The beta is 2 pi by lambda into lambda by 4. So lambda get cancelled and it is a pi by 2. And whole divided by R0 plus J into ZR Now the tan 2 pi by lambda is a beta value, and the length of the transmission line here is lambda by 4. So lambda get cancelled, and 2 with the 2 2's will get. So Zin is equal to R0 whole multiplying with ZR plus J into R0 tan pi by 2. And similarly here also the R0 plus J into ZR tan pi by 2. Okay. So what is a tan pi by 2 is infinite. So whenever you can keep the tan pi by 2 here itself, infinite plus anything is infinite, and infinite plus anything is infinite. Infinite by infinite is undefined. So take the common of tan pi by 2 on the numerator and the denominator, then becomes R0 into ZR tan pi by 2. Tan pi by 2 means infinite, plus J into R0 whole divided by, and here also take the common of tan pi by 2. Now it is a R0 by infinite plus J into ZR. So 1 by infinite, the value is 0. So Zin is equal to R0 into 0 plus J R0. So J into R0 whole divided by 0 plus J into ZR. So JJ get cancelled, and it becomes of R0 square, and we can change this as ZR as RR. Zin is equal to R0 square by RR. Okay, so Zin is equal to R0 square by the ZR in the quarter wave line of transmission line. Got it, my dear students? Thus, the equation 3 is similar to the equation of the impedance matching using the transform. Zin is equal to R0 square by the ZR. Thus, a quarter wave line may be used as a transformer for impedance matching of load ZR with the input impedance Zin. So the quarter wave line is used to transform the impedance matching. Okay, impedance matching of ZR with input impedance Zin is equal to ZR. For the matching impedance, R0 is equal to, so we got the equation is Zin is equal to R0 square whole divided by ZR. Now I can write as ZR into Zin. The product under root is equal to R0. Okay. A quarter wave line can transform a low impedance into the high impedance and vice versa. Thus, it can be considered as impedance inverter. Okay, for the matching impedances, ZR and Zin in the line with characteristic impedance R0 may be selected such that the condition is satisfied. R0 is equal to under root of ZR into Zin. A quarter wave line can transform a low impedance to the high impedance, vice versa. It can be considered as a impedance inverter. Hence, an open circuited lambda by 4 line gives zero input impedance, while a short circuit lambda by 4 line gives infinite input impedance. So the open circuit, the quarter wave line gives the zero input impedance, while short circuited the lambda by 4 line gives the infinite impedance. Thus, a short circuit quarter wave line becomes as an open circuit, and at the other end, while the open circuit quarter wave line behaves a short circuit at the other end. Okay, the open circuit is a 0, and short circuit gives a infinite value. The quarter wave matching section has a number of applications. One of the important applications is the impedance transform in coupling a transmission line to a resistive load, such as an antenna. So you'll get this in the antenna and wave propagation. So up to this, you can know the lambda by 4 transmission line is nothing. You can call it as an impedance matching. You can transform the low impedance to the high impedance and vice versa, and thus is also considered as an impedance inverter. A quarter wave line may be used as a transformer for impedance matching of load ZR with input impedance Zin is equal to ZR. Okay. Now, next one is a half wave line. Half wave line. Now it is a lambda by 2. The same equation you can use. Zin is equal to R0 ZR plus G into R0 tan beta into S divided by R0 plus J into ZR tan beta S, where S is the length of the transmission line, assuming here half wave line. Okay, beta is equal to 2 pi by the lambda. Beta is equal to 2 pi by lambda, and the length of the S value here, S is equal to lambda by 2. That is a half wave line. Previously, we considered the lambda by 4. It is a transform of the impedance matching. And in that, previously, the 8th wave line, the lambda by 8 length transmission line. It is equal to the R0. Zin is equal to R0. Now it is a Zin is equal to R0 squared by the ZR. Now let us see in the half wave line what is the Zin is equal to. After substituting the beta and the length, Zin is equal to R0 ZR plus J into R0 tan beta is a 2 pi by lambda, and lambda by 2. Lambda get cancelled, and 2 also get cancelled. And Z, not the Z, R0 plus J into ZR tan beta 2 pi by lambda, and lambda by 2. 2 get cancelled, and the lambda get cancelled here. That is equal to R0 ZR plus J R0 into tan pi whole divided by R0 plus J into ZR tan pi. So what is the tan pi? Sin pi by the cos pi. Sin pi is 0. You get the 0, the second term. So Zin is equal to R0 into second term becomes a 0 value. So ZR plus 0 pi in the denominator also R0 get cancelled. The Zin is equal to ZR. When we consider the half wave line, input impedance is equal to load impedance ZR. From this equation, it is clear that the half wave line repeats its terminating impedance. It is clear that the half wave line repeats its terminating impedance. In other words, the half wave line may be considered one-to-one transform. One-to-one transform. The half wave line we can consider it as a one-to-one transform. The main application of a half wave line is to connect a load to a source where the both of them cannot be made adjacent. In such a case, we may connect a parallel half wave line at load point as shown in the figure here. Is a lambda by 2. We can take a suitable measurement as half wave line repeats its impedance. Nothing but here we can say it is a single stub and the double stub is it is a single stub. A single stub line or single stub matching on a line. The other topic now the three lengths we consider to find out the input impedance Zin is equal to. We got when we consider lambda by 8 line, Zin is equal to R0 and when consider the lambda by 4, the Zin is equal to as impedance matching ZR R0 square by the ZR and lambda by 2 half wave line, the Zin is equal to ZR. Okay. Now we go for the another one is a single stub matching on a line. Single stub matching, where a high frequency line is terminating in its characteristic impedance or not, it is operated as a smooth line. Under such conditions, reflections are absent, hence we get a maximum power delivered to the load and hence efficiency. But in practice, the load such as antennas do not provide the resistance equal to the R0 of the line, hence it is necessary to add some impedance matching sections between the line and the load. Okay. When a high frequency line is terminated in the characteristic impedance or not, it is operated as smooth line. Under such conditions, reflections are absent as we get a maximum power delivered at the load. Or it has hence the efficiency, but in the practice, the load such as antennas do not provide the resistance equal to the R0 of the line. Hence, it is necessary to add some impedance matching sections between the line and the load. Okay. Necessary to add it is necessary to add some impedance matching sections between the line and the load, that whatever we are adding the impedance matching sections between the line and the load, such a load appears as the resistance or not to the line. As we have already discussed, the quarter wave line or the trapped line may be used as a impedance matching sections. Quarter wave line, it says that it is a impedance matching section. So in other method, to achieve the impedance matching, it is used as the open or closed stub lines. In this method, a stub is suitable length is connected in the parallel with a line at certain distance from the load. You see here is a transmission line. From the load, you can assume a certain distance of S1. Totally the length is S2. You can keep the stub line is at the particular distance from the load, that is S1 here. The another method of achieving the impedance matching is used to open or closed stub lines is a closed In this method, a stub of suitable length is connected. A stub of suitable length is connected to L in parallel with the line and a certain distance from the load. The distance from the load and it having its length of the stub. By using such stubs, anti-resonance is assured, providing the impedance at resonance